Hi, good morning. I was afraid no one's gonna show up, but great. I was afraid no one was gonna show up, but great. All right. All right. Crack. Let's see. Crack. Make change, and then longest common subsequence.
I got a question.
Yeah.
So for my like fill color one, it works. It's just if I click on and that's probably because of Stack Overflow, but it like if I click the white, like a really big rectangle, it takes forever, and that's probably because it's every single recursion is doing 4 every single, so it's probably doing way too much. Is there a way I can optimize that, or is that just kind of
So that's fine, but just make sure that you aren't going in a loop, because what sometimes happens is if you don't put the base case correctly, then a pixel calls its neighbor, but then that neighbor later calls the original.
Yeah. But I mean, it works, right? If I do smaller ones, it works perfectly, and as I go up, it takes a little longer. But then on the really big squares, it might take a while. Or if I hit the white, I mean, obviously that's just huge. That's a huge rectangle.
They still have that animate button, right?
Yeah. Oh.
Can you see it animate or no?
Yeah. But I haven't just messed around with that.
Okay. Yeah.
But maybe you can go just get my code checked out to see if there's any way I could optimize it.
Okay. Sure. Mostly it's just the white space. We don't really care about that because sometimes there are really a lot of sections. Hi,
I'm Nan. I just switched into your section. And then this is Davia. She just.
Yeah, take a seat. And then we'll get started. So ours is the SCPD recorded section, so you're on video. Alright, so
don't curse because you can hear that. I found that out.
Yes.
They really up your volume on your voice.
Yeah.
It's fun to listen to yourself on video because you sound really different.
Last spring, I remember, this is really funny. So the instructor, Chris, released the midterm grades during class, and then you can visibly hear just swearing in the classroom, and then Chris was like, "Uh-oh." Yeah. I think it's on the meme page actually from 1 year ago. If you dig deep enough, I'm sure you can find it.
Memes, right?
Yeah. And then during our during the section leader meeting, the instructor Chris, he opened the meme page and he played it out loud. He's like, so that happened in my class. Yeah. Okay. So let's just jump right into it because today is literally the most important section, probably. Okay. So I'm just gonna jump straight into it. Today we're gonna cover recursive backtracking. This is the second to last major topic before the midterm. Next week will be pointers, and you do have to know some basics of pointers for the midterm. Okay. The midterm is 2 weeks from now. 2 weeks from today.
Week 6.
Week 6, yeah. So
it's in section?
It's at night.
At night?
At night, yes. I think it's 7 to 9:30. Yeah.
Does it normally take the full 2.5 hours?
Yes.
To do it?
Yeah. So I'll tell you in advance that Marty and Julie's exams are, in the past they've been kind of long. They're around you can see the practice midterms. You can see that they're kind of long. So you will probably need the whole 2 hours and 30 minutes. All right. Cool. Hi. So
Oh no, I'm here. It's good.
let's see. So only 2 of you showed up. There was 3 people who showed up last week, but only 2 of you are here right now. Can we just go around and say your name, and then so we know who everyone is? Yeah.
Hi, Sander,
Eric,
Kevin,
Asia, Nan,
Divya, I'm free fresh.
All right. Oh, cool. All right. Well, yeah. Welcome.
You're what?
Well,
Sorry?
Free fresh?
like prospective freshman. It's
yeah.
Oh.
All right. Welcome. I'm glad you caught us when on a day where the caterpillars aren't out yet. All right. So welcome. This is so SCPD students who have just coming. We're gonna do recursive backtracking today. This is literally the most important topic of at least the first half of the course. So let's get started, okay? So the key idea of recursive backtracking, well, anyone want to tell me what is the idea of recursive backtracking? What's the goal at the very end of recursive backtracking? If you had to summarize like what all the examples Mari or Julie has done in class this week, what was it?
It's kind of
Exhaustive search.
Okay, yes, exhaustive search. That's one of them. Exhaustive search. And what does exhaustive search basically mean?
Like with her example on Monday with like counting up all the words.
Yeah, yeah. Exhaustive search, the idea is you are given like some sort of condition, and then you want to exhaustively search every possible thing that might fit the condition. You just try all of them and see which one satisfies the condition. Okay, yeah. It's exhaustive because you just literally try everything. And then there's a second type of problem that we've done. It's technically we call recursive backtracking, or let's just call it backtracking. Technically, we put it as like something that's like a different kind of problem. These are really similar. The only difference is for backtracking, you just want to see if one such thing exists. All right. So exhaustive searches would give you a condition. You have to find, maybe print out all the ones that work. For backtracking, the idea is we give you a condition. You just have to find one that works. Once you find one, you can stop. Okay. Obviously, if you haven't found one, you have to keep looking through everything. Okay. So if you like don't find anything, backtracking kind of searches the same thing as exhaustive search does. It has to search everything before it says for certain, no, I have not found the answer. Does that make sense? All right, yeah, cool. So these are the two main type of problems, and in class, you've seen like a really like a big like a high level template of what a exhaustive search or backtracking algorithm usually looks like, right? What's like that template? That's good. How about we're gonna for a recursive function, because these are going to be recursive functions. What do you need first?
If.
What would the if be considered? The base case. Exactly. Yeah. So yeah, this is a recursive algorithm, so you're still going to need a base case. And then recursive case. Yeah. Okay. But then in the recursive case, there are, I'd say, 3 main steps.
Yeah, you can kind of go down, then go back up, and then go somewhere else.
Yeah, exactly. So the going down step, that's called the choose. Choose. You mentioned going back up, that's unchoose?
Yes.
Okay. What's the step in the middle?
Explore.
Explore, exactly. All right.
Wait, what's the bottom step?
So the bottom step is called unchoose. Yeah. Okay. And we'll see an example of like how this might be useful. All right. So it's easier to explain this by jumping straight into an example. So let me quickly pass out the handouts. Can you pass these handouts around? Thanks. All right. Let's start with question 3.
I watched it.
Okay. So the idea of recursive backtracking is you're usually given like some list of choices, and then at each step you want to make choices until you have like a full set of solutions. Then you can check if that set of solution works. Okay. So for example, you're often going to be given like a set to fill your solution. You're going to have to fill multiple parts of that solution, and then you're often given different choices. Okay, you're often given different choices, and then you want to see like how many of them. You want to see how many full set of solutions you can find. Okay, the idea is that you want at each step of filling up your partial solution, you need a set of choices. Okay. For example, can someone tell me what was like one example from lecture that Marty or Julie did? What was the one example that you remembered vividly?
There was the one where you gave it. It was like a string of letters, and it was going through and figuring out all the different, or the different like state
Permutations?
Permutations.
Yeah. Okay, so when you're thinking about different permutations of a word, what would your like partial solutions be in that case? When you're going through the algorithm, you're building up partial solutions. What would those partial solutions be? Those partial solutions would just be, for if you wanted to.
Would just be different.
Right. When you wanted to do like, if you wanted to find all the permutations of A, B, C, D, E, a partial solution would be like A, B, C. And at each step, to extend the partial solution, you'd add like one more choice from one of those letters. Right? So here, your first step could be, okay, here's my solution. I'm going to put like B in the first step. And I'm going to put D in the second step, and so on. You're going to keep doing that until you don't need to make any more choices. When you're done with choices, then you can check if that is a valid solution. Does that make sense? Okay, that's a little abstract, so let's quickly dig down into like an example, and you can see that in action. Okay, all right. Another thing I want to note is there are, I think, two kinds of backtracking problems that you'll often see. One is called the idea you want to ask yourself is, does order matter? Okay, because whether or not order matters will determine what kind of choices you have at each step. Okay, so for example, let's do this first problem. Okay, so number 3. You don't have to read the problem. I'll quickly explain what the problem does. So imagine you have like a scale. So you have a scale. I guess scales look like that. And then you also have a set of weights. Let's see, you have a 1, you have a 3, and you have a 7. Okay? I'm going to give you a mystery object. Okay, and just secretly, you know that the weight of this is like 3. Okay? And then the question is, can you put these weights onto the scale so that you can like balance the scale? Does that make sense? So for example, if I asked you, if I asked you, is measurable, right? I give you, let's see, I give you these weights. So let's say weights. If I passed in weights, and I said, is 3 measurable? Is 3 measurable? Yeah. How would you measure 3? Yeah, you can put the 3 over here, right? All right. Does that make sense?
Yeah.
Okay. So that was a little easy. Let's think about how about is 8 measurable? How is that measurable?
1 and 7.
Yeah. So we just put the 7 and the 1 on the other side, right? Yeah. Okay. Yeah. So that would be measurable. Something a little more tricky maybe is 6 measurable?
Yes.
How can you measure 6?
Yeah, 7 on the right, and then you put the 1 on the left.
Yeah,
Well,
you can put So don't forget you can put them on either side. So you can put it like this, and you'll see that that it's measurable. Okay. Now,
that's tricky.
okay, yeah. So this is a little tricky. I actually am not sure how you could do this problem iteratively, and that shows why like recursive backtracking is so powerful. All right. There's no like clear solution on how you would like not use recursion to do this problem. But let's see how we could solve this problem using recursive backtracking. Now, you can see that this is a recursive backtracking problem because the answer we want to give at the very end is going to be a true or false. We want to say, given this condition, we have a bunch of weights, and we're also given the mystery weight. Is that weight measurable? It's a backtracking problem because we're going to say, oh, yes, true, or false. It's not measurable. Right? This is going to give you true. This is going to give you true. Can you think of an example where this is not measurable?
12.
Okay, 12. So 12 is, why is 12 not measurable?
You can't possibly get a
Yeah, because our weights don't add up to 12, so you can't ever have 12. Okay. So yeah, this is a backtracking problem. Now, the key idea to thinking about these problems is always draw a tree, okay, a decision tree. Okay, so we're gonna start with this node, and then let's see, we're gonna put our weights 1, 3, 7, and then we're also gonna have the current weight we want to weigh, which is, let's say it was 7. 7, 6. Okay. Now thinking about this step by step, if I just gave you the weights and I gave you a mystery weight, how can you proceed like one step at a time?
You can either go slowly, add on more weight.
Yeah. Yeah.
Or
So this
go up or vice versa.
Yeah, exactly. So this is the key of recursive backtracking. You go step by step, do one step at a time, and then once you make that choice, the choose, then you can just make the recursive call and trust that it will make the other choices for you as well. Okay. So in this example, you can make a choice to put one of the weights, and then when you put one of the weights, then that would give you another subproblem. To see why that is the case, think about it this way. 6, and let's suppose we first took the weight 1, right? Suppose we put it on this side. Okay, how does that change the problem?
It's as if it's a weight 5.
Yeah, exactly. So this is the same scenario as, suppose we wanted to say, is this measurable using these two weights? This is the same problem as saying, oh, I have these two weights. If I just wanted to measure 5, is that measurable? Right? Does it make sense? So we can see that here. One choice could be, oh, we put the 1 on this side. So then our choices remaining is now 3 and 7. But then the weight we want to measure is 5. Okay? What are some other choices we can make?
Put the one on the other side.
Okay, sure, we could put the 1 on the other side. So let's say we put the 1 on this side. All right, if we put the 1 on this side, what would the equivalent problem be down here?
Can we measure 7?
Yeah, 3 says. We try to measure 7 over here, right? So another choice we could have is, let's see, place, right, place left. But then the weight we're trying to measure now is 7. You can see why why is recursion helpful here. This big problem, yes, can be broken out into self-similar problems, right? If you solved this problem, you would know the answer to this problem. Yes?
I don't understand why if you place the one on the right, it's 5.
Let's take a look at the example. Let's see. So 6. Suppose.
Oh, because you have to add, the right side has to, like, with the remainder, like, with the remaining numbers, you have to add it up to 5. To make
Yeah.
sense. Okay.
So think about it this way. Let's say I ignored these weights. If I somehow was able to find a way to measure 5 here, I could just put the weights here and just put it up here, and that would measure 6. Suppose I found a solution here with some weights. I don't know.
Yeah.
Okay, I could just move these weights up here, and you would get a solution for this one.
Okay.
Yeah, this idea of backtracking, of recursive backtracking, where to solve this problem, we can solve 3 smaller problems.
Okay.
Okay. Yes, I hinted there's 3 smaller problems because there's actually one other choice we can make here.
Don't use 1.
Yeah, definitely, because we don't have to use the weights, right? In the examples we did, sometimes we just never use some of the weights. So we can just leave the weight down here, just not use it. So that's also a choice we could do.
How would you here account for physics of the solution like that? You don't place the largest weight on the left-hand side because then you would never be able to.
Let's see. 6. Okay. So you mentioned about like being a little clever, saying, "Oh, 7 should not go on the other side." Yeah. Actually, because in this the correct answer, 7 does go on the other side, right?
No, but on the left.
On this side?
It would never go on the left side.
You want to be careful about that because I can think of one example where it might. So this is not part of this example, but suppose I give you the weights. Let's see. Suppose I gave you the weights. So suppose you had 7, and then you had 5, 4, 3, and 1. Right. I could put the 7 over here, and I could put the 5, the 4, the 3, and the 1 on the other side.
Sure.
Yeah.
It depends on the physics of it.
Yeah. Because that I think that is a little hard to generalize for like any weight. So we're not gonna make that like that optimization. Okay. Sometimes you'll notice that this problem is probably gonna take a long time because at every step you're gonna branch out 3 different more paths. So backtracking algorithms are generally a little slower. You heard people like people have said like, oh, they can't solve chess because chess is like just so big, and the reason for that is every time it makes a choice, it branches out. So as you get more larger and larger, there's like more spaces to explore. Okay, so backtracking algorithms are a little slow that way. Okay, but what's nice about it is they can solve the they are correct solutions to solving problems like these. Okay, cool. Let's see. Let's go back to that example. All right, so we've shown that you can make like 3 different choices over here. Okay, now I have a question for you, and this is a incorrect tree, and I want you to try to explain why this is an incorrect tree. Okay. I'm gonna say 1, 3, 7, 6. One choice I could do is I could put the 1 on the one side, so I could have like 5. How about I put the 3 on one side? I have 1, 7. And then if I put the 3 on the other side, I get 3. I could put the 7 on the other side, and then I'd have -1, which is fine. -1 is fine because later we can put weights on the other side again. Okay, and then I could have like more choices. I could say rather than put the 3 and the 7, I could put the put the 1. I could put the 1 on the other side, so I have 3, 7. But rather than 6, I'd have 7 over here. Okay, and you can notice like, okay, for each weight, we can put them on the left, the right, or none at all. Right? Why is this tree not correct?
Because it explores way too many.
Yeah. Because each level of the tree, you want to just explore one different option. So like you want to do an exhaustive with only one variable, and then keep on going down.
Yeah. Can you see why this might later in the tree there's going to be like repetition? Yeah. Where would you see some like repetition here?
The -1 and the 7, like the last two.
Last two?
They can both, if you then place 1 on the other side, and if you place 7 on the other side, then you get the same solution.
Okay, so let's see. Right. For example, okay, this is good. Let's see. I could put the 1 on the. So here, this path is put 7 on the right, yeah. And then this one is put the 1 on the left. Okay. Here I could put the 1 on the left. Put on the left, which gives me 0. Here I could put the 7 on the right, and that gives me 3, 0. See what we have here? Yeah, this decision tree doesn't work. Marty gave an example in class, and he calls this wasteful. And why this is wasteful is because notice that these two give you the same solution. And you can also see why it gives you the same solution, right? It's doing the same choices. Putting 1 on the left side, putting 1 on the left side, putting 7 on the right side, 7 on the right side. Okay? Now, this is a really common like issue I see like a lot of students make, which is they don't know how to draw that decision tree. And the key idea is how do you make a choice, right? Do you make a choice by thinking about, here we focused purely on the first thing that we see, the first weight that we have in the choices. But here what we decided to do is we decided to go through all of them and try all of the choices. Okay, this goes into the idea of does order matter, okay? oftentimes when you're trying to build up the solution, you want to think to yourself, does the order in which I put the weights matter? So in our diagram above, does it matter if I put the 1 weight or the 7 weight first? Not in this example, right? So when it doesn't matter what order you put the weights, what you want to do is you want, at each recursive step, focus on 1 weight at a time. Because order doesn't matter, the order in which you put the weights doesn't matter, you should go through the weights one by one and put them and make choices on them based on 1 by 1. Okay? So to go back to the example over here. Here's your solution. Here's your solution that you're building up. And then here are the weights that you have. 1, 3, 7. Because the order in which we put the weights in here doesn't matter. Okay, we can see like this is the left, right, none. The order in which we put these inside here doesn't matter. So in recursive problems where the order in which you put in here doesn't matter, you should focus on 1 weight at a time and make a choice based on that 1 weight. Yeah, question, yes?
Is it then often like, I can imagine if the order doesn't matter, you'd have those be sets, like the left and the right and none. And if it's like sets or if it's things you can't sort right, then you can already deduce that the order won't matter. Whilst if it's going to be like a queue in which you put them, then the order would potentially matter.
Okay, I think what you're saying is that you're suggesting we can just think of it like a set. And then for each one you can say, oh, do you want to include it or do you want to exclude it?
Yeah, kind of. But like, just if you have a problem and if they ask you to return a certain set, then you know the order won't matter.
Yeah. Sometimes the question itself gives you a hint as to does the order matter or not. Sometimes you just want to think about it yourself as, like at the very end, does it matter if I put the 1 or the 3, the 7 in at different times? Okay. Now you want to be careful about just thinking, oh, should I include the 1 or should I exclude the 1? That often works when you want to like find a set that works. But in this example, you can't just say, oh, do I include the 1 or do I exclude the 1? Because when you include the 1, there's 2 ways you can include the 1. Right? You can put it on the left side or the right side. Okay? Does that make sense? All right. So, and then taking this diagram, we can move 1 step further, right? After we've made 1 choice, how do you make the other choices?
Do the same.
Right? So we were focusing on the 1 weight, now we focus on the 3 weight.
We do 3.
Yeah, so we could have, so right side, it would be 7 with 2. Let's see, left, none. 8, 7, 5. And this, like, you can do this for all of these, right? Okay? When does this search stop? So this is going to keep going until it stops at some point. When does it stop? Yeah, when you get the empty set, right? So if I let's do this one. This was going to give you 3 choices. It's going to be -2, 12, and 0. Nope, not 0, 5. Empty set, empty set, empty set. Okay. As the choices keep being made, at the end you'll find a time where you have no more choices left. What happens in this case?
It'll reach your base case, or it'll start backtracking up.
Yeah. So yeah, exactly. So yeah, once you reach this point, you're like, okay, no more choices can be made. Now I can check, did my answer work? Okay. Did any of these work?
No.
Yeah, because at this point, what it means is you've used all the weights, but you still have like an imbalance on one side. So in this case, you say, oh, this solution doesn't work. So I'm going to undo my choices. I'm going to go back upwards. Okay. What recursive backtracking does is it's going to make a bunch of choices. Then when those choices don't work, then you go back up the tree and you try some other choices. Okay. Now, remember from last week, hopefully y'all went to section last week, but from last week, you know that when you write the code, it's helpful not to think about the whole tree, because the whole tree is super confusing, right? You sometimes think, oh, okay, I've done one step. How do I do the second step? All right. When you actually write the code, only think about the first step. Okay. So let's go up. All right. This is fancy. All right. So in this example, how would you go down one of these steps? So the choose step is always, given we're at a certain node, how do I make a choice to go down to a node lower than us? How can I make a choice here?
You can just DQ.
Okay, so take the first weight and
Try every explore. You'd explore all possibilities. You can do it this way.
yeah, exactly. Remember for the choosing, not only are you taking the weight out, but you're also choosing which side to put it on. Right? So we take the weight out and we can put it on left, right, or none. After you make the choice, you've started from one node and you've gone down to one of those nodes. What can you do at one of those nodes?
Do that
Okay.
again.
Yeah.
With another weight.
Yeah, because don't forget the function. What the function does is it starts you at a node and it searches through all the nodes below. When you make the when you call explore, it's essentially calling you've gone down to a node on the second layer, and you're now just continuing to explore everything below. Now you have no idea how it's going to do that, but you can trust that this is recursion. Take the leap of faith. Trust that your function already works. The function that you wrote to solve, starting at the top node, you can essentially say, oh, it's the same as solving the function at the 3 nodes below. Okay, so we can have essentially make recursive call. Okay, the key idea of the recursive call here is you have to make the recursive call on the right parameters. So the parameters aren't going to be the same. You can notice that the numbers aren't going to be the same, right? Okay. All right. And then the key idea for unchoose is once you've committed to a choice, so let's say we committed to putting the one on the right. After we've explored everything underneath that, we need a way to get back up to that node. How do you get back up to that node?
Unchoose.
Yeah, unchoose, but then specifically starting from over here, how do we get back up there?
Take the 3 off.
The reverse.
Like put the
Yeah, put the 1 back in.
Yeah.
All right, put the 1 back in, and then add the 1 back to the 5 to get 6. All right. The idea for unchoose is you want to put the weight back in. Okay. This step is very important, and students miss this a lot. If you don't make this step, it's impossible to go back up the tree to try some other steps. Okay. Now, no one mentions this last step, but the last step is how do your recursive calls are going to give you like answers to those 3 nodes. Are these 3 measurable using those weights? Now you want to think, how do I combine those choices? For example, if I back up here, right, if I made this choice, versus this choice, if I make the recursive call on this is going to return something. What is it going to return? False. This will return false. Okay, you don't know that, but you secretly know, oh, this will probably return false. Okay? If you take the recursive leap of faith, trust that if you make a recursive call on this, it will give you the right answer. Suppose it was false. This is going to give you true. You can already see it's going to work because of the 7 here. How about this one? False. Right? You can't form 6 using 7 and 3. Okay? Once you make the recursive call, trust that this is going to give you false, this is going to give you true, this is going to give you false. All right? Given these 3 results, how do we combine them to know what the answer we have to return is?
Or.
Okay? If one of these work, then we know that this one works. Right? Because we can put the one on right, left, middle. But once you've tested all of them and you've found that one of them works, one of them returned true, then you can say, oh, this whole thing is true. Okay, so yeah, you're exactly right. Use or in this example. Okay, let's try coding this up. I didn't fill out the base case, but you can think what the base case is right now. All right, is measurable. Okay, so the function we're going to write is measurable, and it's going to take in a vector of ints, weights, and then it's going to take in int, I'll call it weight, mystery. Okay, so we have a base case, and we have a recursive case. Let's do the recursive case first, because we've kind of fleshed that out already. Oh, don't forget, it's not bool. It's not void. It's bool, because we want to return true or false. Okay. Now, in the recursive case over here, what are the 3 steps we have to do? Choose. Okay, so for choose, how do we do that choose step?
We take the first statement.
Okay, so how do you take out the first weight?
Vector.
Mhm.
Yeah.
Okay,
Sessions or whatever.
so int weight is, well, let's say call it current for next. And that's equal to, how do we get the first weight? Weight 0, yep, that gets you the first weight. What other steps do we have to do to get to this node over here?
Choose.
We also have to remove the 1, right? From the vector itself. Weights dot remove 0.
Is there a way you can do that in one step?
I don't think so. Maybe,
You
but
just pull it off.
Like pop. Wait,
Huh?
that's
That's
with
cute.
That's
Yeah, that's
cues.
just what the. I just was running it down.
Maybe.
But it's all good.
okay, yeah, it's totally fine if you write it like this. Okay, we also have another choose that we have to do, right?
Sorry?
We also have another choose we have to do, because we've now taken care of this vector over here. How do we get to these numbers down here? Okay, so to get to this one, what do you do with, how do you get to this 6 to the 5? Subtract, right? Okay, so we're going to have, our new weight is going to be mystery minus next, right? And then how can we call explore on this?
Just is measurable of
Yeah.
weights. Mystery.
Is measurable of weights and mystery minus next. All right, if you make this recursive call, it's going to make this call over here.
Yep.
Okay.
Do that again with plus next, and then just.
Yep,
Mystery.
exactly. Measurable plus next, and then there's also one more, which is you don't put the weight at all. Measurable weights mystery. Okay. Now these 3 are going to return booleans. What do we do with these 3 booleans? Or them.
Yeah.
Okay. So my question is, does this work? If I just say, I just take the booleans and I just put an or between all of them, does that work?
No.
Why not?
You didn't branch out.
Because it doesn't what?
It doesn't completely branch out.
Yeah.
Just one line.
So you're exactly right. So when you make the recursive call over here, this gives you a recursive call. It's going to return false, right? But then the thing is, when you make the 3 recursive calls, when you make the 3 recursive calls, like for example down here, right? This can give you something, and then you have to be able to return back up here to return something, right?
Yeah.
But we're missing one step in that process. The unchoose. Because notice that in this example, once this function returns, what is weights?
It's the one with 2. It's the one that's 2.
Yeah.
Numbers in it.
The first element that we removed from weights is no longer there. But remember, because later on we have to go back up the tree. For example, after exploring down here, this is going to return some result over here. But then we have to put the 3 back in, so that way we can also put the 6 in here, and so on. Okay? Yeah, don't forget you always have to put whatever changes you make to your data structures back. so that it can properly explore the other ones. Okay? Yes, question?
If we weren't passing by reference, then would it be necessary to?
Yeah, that's a good question. So if you aren't passing by reference, then that would not be necessary. But you always want to do it by reference because remember, you don't want to copy data structures. Okay? All right. So how can I fix that?
Add weights
Mhm.
or add next.
Yeah, you're exactly right. We can't. Let me save this in a Boolean first, because you can't just return over here. You have to first say weights dot add next. All right, is this correct?
Would you want it? It's the order doesn't matter, right? It's like it doesn't matter that you added it to the back of the vector.
Yeah. So suppose the one over here, instead of adding it to the front, we added it to the back. Would that work?
Yeah.
Because if you add it, if you add the one in the back, later it's gonna search. Like this is gonna check for the
3.
let's see. If you let's say down here, suppose we added the 3 here at the back, then this is gonna be flipped around, right?
Yeah.
And this is gonna be flipped up down here. Yeah. And then the search over here will give you, instead of 3, 7, it'll give you like some other order. Yeah. I think for this problem, it may or may not matter. I'm not sure if it does. It's always a good habit. Make sure that when you put stuff back in, put it in the exact same order. Okay. So this for sure works. I'm not sure if adding in the other one.
Well, it wouldn't work, right? Because it would just every time it would go
And check.
and check the first
Yeah.
element and so
So
stay
you
stuck
would
in that
want
way.
add
Yeah.
it to the back. Okay.
So please work. Okay. Anyways. Oh, maybe my
I think it's measurable without the E.
I think.
All right. Anyways, so you can trust that this will work probably. All right. Yeah. There you go. That should work. Okay.
Is it because you're
Oh, yeah.
supposed to add it to the back?
Yeah. So you definitely want to add it to the front, but you always want to restore the data structure. So if we removed it from the front, then you want to add it to the front again.
Yeah, we didn't have our base case.
Yeah, we forgot the base case. All right.
So it's empty.
So let's see. The base case is if the vector is empty. If weights is empty, then if weights is empty, what should you return?
Return.
Return mysteries.
Yeah, so return if mystery is 0. If mystery is 0, that means we found a solution where it fully balances. Return mystery equals 0. Remember that this gives you a Boolean. Mystery equals 0 gives you a Boolean. Okay? Actually, does this work?
No. Wait, I don't know.
Actually, never mind. Trick question. I think it does work. I think it does work. All right. Let's see. Is measurable, is measurable, is measurable. Okay. Let's see if that works. I think that should work. All right. So yeah, and I don't know. I think if you add it to the end, I don't think it'll work because then like the order of the ones at the top are switching, and then you might like duplicate some calls, but like not duplicate some calls. Yeah. So I think if you just add next, I think this doesn't work. Okay. All right. Oh, I guess it still does work. All right. Hey, in general, it won't work because in 8 minutes we're gonna solve a problem where order does matter. Okay.
Oh, so because order doesn't matter here, that's
Yeah.
why it was working.
Yeah. Let's quickly do an example where order does matter. Okay, and this is a very relevant one. So the question is number 6, called crack, and the idea is this: you're given a function called login, which takes in a password, and it gives you true or false. Okay. Think of calling this function as trying to log in. Okay, so login 1 2 3 4 5. That's I'm trying to log into some account, and it's going to say true if it worked, false if it didn't work. Okay, and the idea here is you're going to write a function called crack, bool crack, with an int max, which essentially says, okay, take in a max parameter like 3, and what I want you to do is try every password up to length 3. So try every. So I think we're going to restrict to alphabetical characters only. Try every password up to max. Okay. So with every password we get, we're going to try to log into that, and then this is essentially doing a brute force. Okay. I'm going to try every possible combination and find a way in. Okay. Does that make sense? That's essentially a function that we're trying to write. Now let's draw a decision tree. Okay. So so how can you think of this question as a making choices at each step? How is this problem how is it similar to the other problem? Other problem we're like taking choices and we're putting them into like our current solution. How can we make choices in this one as well?
Or you start with like I guess A. You do that. You branch off with choosing A, and then you can do that for every single one on that first level. And then just keep on adding like another character.
Yeah. So you can think of our choices as now A, B to like Z, and then here's the choices we're gonna make, and we're gonna make a choice to put. We're gonna make choices in here to put them into our string. This is gonna be our password. Does the order in which we put these in here matter?
Absolutely.
Absolutely, right? Because A, B is not the same as BA. All right. So in this case, order does matter. So when order does matter, how you want to make the choices is at the very next box, like this box, which choice do I put in? Notice that this is different from the other one, right? The other one is take each one over here and decide whether or not to put it in here or don't put it in here. That only works if the order doesn't matter. Here, because the order does matter, you have to go position by position and say, okay, which one do I put in this position? Which one do I put in this position? Okay? So repeat that one more time, because this is super important. When the order does not matter, you can just look through each one here and say, should I include the A? Should I not include the A? Should I include the B? Should I not include the B? But when the order does matter, you have to go position by position and make choices with each position. Okay?
Okay.
Okay. Question? Yes.
So when would position matter and when would position not matter?
Yeah, that depends on the question. So you're gonna have to read the question and figure out like in the solution that you print, or that you return, or that you find, does the order in which you make the choices matter? So here you can think, okay, I'm trying to form a password. I'm trying to form all the passwords. Now, because the letters in the password does matter, right? Yeah. So in that case, like you do have to make sure you have order. But for the weights one, it doesn't matter which order we put the weights. So that one doesn't matter. Okay. All right. Crap. So let's see. So we start with the empty string. What choice can we make at the empty string?
Is this?
We're trying to crack a password.
Sorry, are we given a maximum length?
Yeah. So you're also given a maximum length. Yeah.
Just pick any character.
Okay. So there's not 26 times 2 because we're also doing uppercase ones as well. So capital C. Okay. So we have a bunch of choices, and what do we do with? Yeah, you can repeat. So there's a reason why I'm not writing like the choices out explicitly, because at each step we can choose A, B, or something to Z. Later on, even if we chose A, we can still do more A's. Yeah, so repeats in the password string are allowed.
So in this case, we don't need to do anything for unchoose, right?
That's a good question. So
Taking things out.
depends on how you add the string, how you add the letter in. So I'll demonstrate that in like 2 minutes. Yeah, because it depends on whether or not you change the string or if you pass in a copy of it. I'll show that in a second. Okay, but here.
The other option is not including you have A, include A.
Yeah. So don't forget, because the order does matter here. So if we decide to put A, we can still. If we decide to not put A here, later on in the other steps, we can still put the A in the other positions. Remember, when the position matters, when order does matter, you can't go through these one by one and say include or exclude. You have to go through each position and make a choice there. Okay? Because just saying include, exclude here, that kind of doesn't really You don't know which position you're putting it in because that does matter. One thing I've seen some people do is they said, okay, I'm going to focus on A. I'm going to choose which position to put it in. So I'm going to put it in some random position over here. Does that work? It might. Probably won't. Depends on the question, but this typically does not work. Oftentimes because you don't even know what the length of your password is going to be. So you have no idea where you're going to put this here. Okay? It also makes it really hard to track. In kind of like recursion last week, we always focus on the first one, right? So in general, always focus on like, always put make the choices in order. Don't just randomly stick things in here because then makes it hard to track where do we put the next one. Okay?
Should we also include a choice to like stop? Basically.
Yeah. So that would be, yeah, that's a good question. We're gonna try logging in at each step, right?
Yeah.
Yeah. And then if logging in succeeds, then you can just stop. So yeah.
Should we do that before recursive call?
Yeah.
This time?
So that would be a base case.
Yeah.
Okay. All right. So you can have in this example A, B, Z, and then what more choices can you make at this step?
Second.
You can choose another A,
Yeah.
A, B, and you're gonna keep going on, right? When do you know when to stop?
When it works.
When it works, or
Or when you reach the max length.
when you reach the max length, then you should go back upwards, right, and try the other choices. Let's quickly write that. Bool, crack, and max. Okay, and then let's see. All right, what do we need to put as parameters here?
I guess you would call the.
You have your current kind of
Current string, right?
Yes.
Yeah, the current string you have so far. But the thing is, our function doesn't have that parameter.
We need a helper function.
Yeah, exactly. So remember the concept of a helper function? It's okay. So when you need to keep track of extra information more than the parameters give you, then you're gonna have to. We're not allowed to just change the parameter to say password or current. Okay. You have to actually declare another function. Bool crack helper string current. Okay, and then let's see. So what is our base case over here? If so
So if like you can put in the password.
yeah, so
if you put in your current.
So if one of them works, then you
Yeah,
can just return
return.
true.
Yeah.
Otherwise, if the current password dot size is equal to length, which means we tried the current one, it doesn't work, and it's also already too long, then return false. Otherwise, you essentially just try all the characters. There's a clever way of doing this. Char ch equals. I can start at A. I can go less than or equal to lowercase z. So don't do capital Z because
Let's do two different ones.
because the lowercase and the uppercase aren't like they're not continuous. Yeah, so I'm gonna start from A and go up to Z and ch plus plus. I'm gonna zip through this because this is sort of not super important. The looping to the characters, and then at each step we can just add the current on there, right? To answer your question about do we have to unchoose? If you do current plus equals character, then when you make the recursive call, you have to remove that character, right? Here you have to say remove current dot length -1. Okay? Does that make sense?
Yeah.
Yeah. If you change current, then you have to change it back. But another way you could do this is when you make the recursive call, crack helper, you could just you can not actually modify current, but you can just when you pass in the parameter, add the character onto current. So you're not actually changing current, but it's just when you pass in the parameter, you're passing in a modified version of current. Does that make sense? Okay. Yeah. Okay. It's too bad we don't have time, but the solution should look something like this. Okay. So remember to in backtracking problems, you always want to wrap the recursive call in a if statement because if one of them works, then you return true.
Yeah.
But if it doesn't work, then you should keep searching. Okay? So it's incorrect to write just return crack helper. Okay? It's not correct to just return that because you should only return if it's true, if it worked, if it's true.
Yeah.
Right? And then I'm going to say return false down here as well. Okay? And I have to do it again for the uppercase ones. So, okay? Yeah, but basically that's it. Current plus. Oh, actually, in this question we have to return a string. But anyways, yeah, in this question we're supposed to return a string.
So
Yeah.
I mean, I like it's nice that we have a helper function, but like for the homework, it was like, why couldn't we just had an extra parameter to use in our actual?
Oh yeah. Okay, so that's a very good question.
Whatever.
Yeah, that's a good question. So this is an issue that you will see more next week, where the thing is when you're told to write, when someone asks you, can you write a function for me?
And they just want this.
Yeah, they want that function. You don't want to expose your other parameters.
Okay.
Okay, like if you change that parameter, then suddenly I can call. Let's see. Are you referring to the fractal, the subfill one?
Yeah.
Okay. If you added other parameters, then when I call the function, I can also add my own parameters.
Okay.
Yeah, which wouldn't make a lot of sense. All right. You don't want to expose your parameters that are not part of the implementation.
Okay.
You're given. Okay.
Thank you.
All right. Cool. Today was a little rushed. I'd hope to get through more, but
I was good that you went through that. I think that's the most important part.
the most important thing I'd say in backtracking is make sure you figure out the order. Does the answer have to be in the order or not in the order? Okay? If it has to be in order, then you go through each position and you make a choice based on that. If it's not in order, you go through the choices and you decide include or exclude or something else. Okay? Cool. One more suggestion, and that's sometimes I'd cover this question called longest common subsequence. I strongly suggest you do. It's a little hard to cover in section because it's really hard, but I strongly suggest try to figure that question out. That question, usually it's not important, but I don't know, one quarter where when I happened to teach it, a really similar problem came up on the midterm, and my section was the only one who got it right. So yeah, cover longest common subsequence. It's a really cool question. It's really challenging as well. Okay.
Do the section.
Solutions, yes. So I only have 2 out here, but since we're in Gates, the solutions are also right outside they're right outside the office in the left corner over there. Do you know Kate's office hours? Kate's office hours are in like that corner over there, and there's like a pack of solutions in front of the office.
Okay.
Yeah, because can you just go there and pick it up.
They're also online.
Yeah, they're also online. Yeah.
Okay.
But I have solutions over here. I have 2. You want a copy? Okay. All right. Thanks for coming.
I have a question.
Yeah.
I was
Cheers,
wondering
y'all.
about, like,